Today I am going to discuss about electromagnetic waves, and this is chapter number 9. And initially I will discuss the electromagnetic waves in one dimension. The first thing is, what is wave motion? So I have defined a wave as a disturbance of a continuous medium that propagates with a fixed shape at constant velocity v. Let's start with a simple case. This is a very simple case, and here the shape is fixed and this shape is moving with constant speed v. So if time is equal to 0, this shape is f of z. Mathematically we can represent this f of z and 0. And initial shape of a string is g of z, which is equal to f of z 0. So this is the condition for initial when time t is equal to 0. Then the question is, what is f of zt after some time t? What will be the mathematical expression of f of zt? Evidently, f of zt, which is equal to f of z minus vt of 0, which is equal to g of z minus vt. So if this is moving with constant speed v, then we have velocity v at some time t, then z minus vt. For example, this expression tells us that the function f of zt, which might have depended on z and t in an old way, in fact depends on them only in the very special way combination. For example, this is the z minus vt. F represents wave traveling in z at speed v. For example, let's suppose we define some functions. If a and b are constants, then f1 of z t, which is equal to a e to the power minus b z minus vt. If we have this kind of uh, uh, expression z minus vt, then it means that this is a traveling wave. The wave is traveling with velocity v in the z direction from left to right. Similarly, f2 of zt, which is equal to a sine b of z minus vt, this is also a traveling wave. f3 of z t, which is equal to a divided by b z minus vt plus 1, this is also a traveling wave. But these two, f4 of zt and f5 of zt, this is equal to a e to the power minus b. This is not in the form of z minus vt. So these two are not traveling waves, but these are the traveling waves where the wave is moving with velocity v at along the z direction. Now the question is, why does a stretched string support wave motion? I have shown a stretched string like this, and there is some tension in this string. There is some vertical component. This string makes an angle theta with this axis, and this also makes an angle theta prime with this axis. Then we have two components. One is the t sine theta, the vertical component is in the downward, and t sine prime, which is in the upward direction, and the horizontal component cancel the effect of each other. Then from the net force on this segment of string must be equal to delta f, which is equal to t sine of theta prime minus t sine of, because one force is in the upward direction and the other one is in the downward direction, then the net force must be equal to the subtraction of these two components. Now, if the distortion is not so large, if the distortion is not so large, then sine theta prime approximately equal to tangent theta prime, and sine theta approximately equal to tangent theta. Then putting the value of these sine theta prime and sine theta in this equation, it means that delta f, which is equal to, if we take t common, then this is t tangent theta prime minus tangent theta. And okay, let's see here. This is a tangent theta. Tangent theta actually the differentiation of some function with respect to z, for example here, and here there are some changes occur at this z plus delta z, then we can say that some changes in a function f with respect to z plus delta z, then this tangent theta prime, which is equal to this, and this tangent theta, there are some changes at this point z, then we can represent this in this form. Further, if I represent this with f prime, because this is a differentiation with respect to z, and it is a function of z plus delta z, minus this is f of z, then mathematically if I divide this with respect to delta z and if I multiply this with delta z, then this function, this expression, this is equal to, by mathematically this is equal to f double prime of z. And f double prime means differentiation, two times differentiation with respect to z. So this delta f, which is equal to t partial square f divided by partial z square, and multiplied by this z. This is a mathematical expression. You can find this everywhere in mathematics. So this is equal to f double prime, and f double prime means partial square f divided by partial z square. And I consider this as with equation 1. If the mass per unit length is mu, if the mass per unit length as mu, I have represented the mass per unit length by mu, then from Newton's second law of motion, then from Newton's second law of motion, this delta f, which is equal to mu delta z and partial square f divided by partial t square. Now I want to compare this. I say that this is Newton's second law. But we know from the previous knowledge that delta F or F, which is equal to ma. This is the Newton second law. And further, this is equal to dv divided by dt. And further, this is equal to m d square s divided by dt square. So, how we can say that this is Newton's second law? And I want to compare this with this, and I will prove that this and this equation remain the same. How? How is it possible? Because this mu delta f, which is equal to mu, I have defined mu. Mu is the mass per unit length. Mu mass per unit length, and let's suppose per unit length as delta z. And this delta z we have also. This and this equation, and partial square f divided by partial t square. This will cancel with this, then this delta f, which is equal to m d square. This is any function f divided by dt square. Now this and this looks the same. So it means that delta f, which is equal to mu delta z partial square f divided by partial t square, this is a Newton's second law. And now I label this with equation number 2. Comparing equation 1 and equation 2, then we can get partial square f divided by partial z square delta z, which is equal to mu delta z partial square f divided by partial t square. This will cancel with this z, and then partial square f divided by partial z square, which is equal to mu divided by t, and partial square f divided by partial t square. This is very important term, and by definition velocity can be defined as tension divided by mu. By definition, we can say that this velocity in the string, which is equal to tension divided by mass per unit length. And then if I put the value of this, then it means that this v square must be equal to t divided by mu. And here partial f divided by partial z square, which is equal to 1 over v square and partial square f divided by partial t square. And this equation is very important equation, and this is known as classical wave equation. This is classical wave equation. This admits as solution of all functions of the form f of z t, which is equal to g of z minus vt. This admits that this all the function will be in the form of this equation, and I call this equation as A. Now, all functions that depend on the variable z and t in the special combination this u, which is equal to z minus vt, and from equation A that last time we have represented f, and if I differentiate with respect to z, then this is equal to partial g divided by partial u and partial u divided by partial z. So it means that I can write this in a chain rule in equation A, and I have already defined u, which is equal to z minus vt. Then partial u divided by partial z, if I differentiate partial u divided by partial z, then this is equal to 1 and this is equal to 0. It means that partial f divided by partial z, which is equal to partial g divided by partial u. And if I again differentiate partial square f divided by partial z square, then we can have the same situation, partial divided by partial z and partial g divided by partial u, and interchange the denominator partial z with partial u, then partial f divided by partial z square, which is equal to partial divided by partial u, and then again write this as in the chain rule, partial u and partial u divided by partial z, and this again equal to 1, and we may have this will be equal to 1, and then it means that partial square f divided by partial z square, which is equal to partial square g divided by partial u square. And now I call this as equation number B. I want to take the time derivative of equation A. Take the time derivative of equation A. If I take the time derivative of equation A, then partial f divided by partial t, which is equal to partial g divided by partial t. And I have again repeat the chain rule, just we have done in this equation, then partial f divided by partial t, which is equal to partial g divided by partial u and partial u divided by partial t. Now, if I differentiate this with u with respect to t, then I will have partial u divided by partial t, which is equal to minus v. Putting the value partial f divided by partial t, which is equal to partial g divided by partial u, and this has the value minus v, then I will write down here minus v. And again, differentiate with respect to time, then this will minus and partial divided by partial t, partial g divided by partial u. And now interchange this, the denominator, partial square f divided by partial t square, which is equal to minus v, and partial divided by partial u, and partial g divided by partial t. And again, apply the chain rule, then minus v, partial u, partial divided by partial u, and partial g divided by partial u, and partial u divided by partial t. Then again we have partial u divided by partial t minus v, then it means that partial square f divided by partial t square, which is equal to v square, and partial square g divided by partial u square. And from this equation, if I calculate partial square g divided by partial u square, then this will be equal to 1 over v square partial square f divided by partial t square. And now I call this equation as equation C. Comparing equation B and C, if we compare equation B and C, then it is clear from these two equations, because partial square g divided by partial u square and this partial square g divided by partial u square, then comparing equation B and C, we can get partial square f divided by partial z square, which is equal to 1 over v square, and partial square f divided by partial t square. And this is again the wave equation. And this equation is whenever the wave is moving from left to right, and this is also true when the wave is moving from right to left, because there is a v square. Then I will define that g of z minus vt, the wave is moving to the left, the wave is moving to the right, and whenever g is equal to z plus vt, then it means that the wave is moving to the left. Similarly, we can also take the wave and a superposition principle, because we can have two or more than waves that they can move, because f a function f of z into t, which is equal to, we can write down this in as superposition principle, g of z minus vt plus g of z plus vt. So this is under linear combination and will hold the superposition principle.